So a very brief review of what we should know about parametric curves. So first of all, what is a parametric curve? That's a curve described by giving x and y as function of a parameter. In this case, I'm calling it t. It could be called anything. And then t could be restricted to be within a range, for example, from a to b. In this case, we would have a starting point at t equals a. So we have x of a, y of a. Then the curve traces its path until it reaches the end point, which is when you plug t equals b. So x of b, y of b. If there's no restriction, then it's the largest possible domain that you can give to the functions x of t and y of t. So in general, for curves, we care about finding the equation of the tangent line, and that requires to find the slope. So imagining that we can express this as the graph of a function, at least locally, then the slope is given by the derivative of y with respect to x. And in this case, we're going to obtain that by taking the derivative of y with respect to t and dividing by the derivative of x with respect to t. That is provided if the x dt is non-zero. Then some questions that you might get asked is to find for which values of t you have a horizontal tangent or a vertical one. So horizontal tangent means slope equals to 0. So this ratio should be 0, meaning dy dt has to be 0, but the x dt has to be non-zero. What happens if the x dt is 0 and then dy dt is non-zero? Then we have a vertical tangent, slope infinity, you can think of. If they're both 0, then we have an undefined form, so it's not exactly clear if we have a horizontal or vertical tangent or what kind of tangent we have. Another thing that we might be asked is to figure out when the curve is concave up or down. That's related to the second derivative. Now here you need to be careful. We cannot just take the second derivative of y with respect to t and divide by the second derivative of x with respect to t. We're going to use the same formula here. So what's the second derivative? That's the derivative with respect to x of the first derivative, dy dx. And this formula, replace y by dy dx, tells you that you need to take the derivative with respect to t of dy dx and then divide by dx dt. So that's how you obtain the second derivative. This is going to be a function of t that you computed with this formula, and then you divide by the derivative of x with respect to t. If that's positive, then you have concave up. If it's negative, you have concave down. Finally, one last thing we should remember is the arc length. So how do we compute the length of this curve? Well, just take the integral from a to b. Those are the restriction on the starting and ending point. And then it's the square root of the sum of the squares of the derivatives of x and y with respect to t. In general, integrals that arise from arc length could be very hard to compute because they involve a square root. So either you'll have some simplifications or you might be required to use a trigonometric substitution.